You typed something to an AI today, a question, a message, maybe just "fix this," and it answered like it understood you. But here's the strange part. A computer has never read a word in its life. Not one. It only knows numbers. So somewhere between your sentence and its answer, your words quietly turned into numbers. In the next few minutes, you'll see exactly how a machine ends up with something that looks a lot like a map of meaning. This is Glass Box, where we make the hardest ideas in AI feel obvious. Today's question: how does an AI turn plain words into numbers it can actually do math on? Last time we watched words look at each other with attention, but before any of that can happen, the words have to become numbers first, because deep down, a model can't add letters, can't multiply a sentence, can't compare two paragraphs. It can only crunch numbers. So the very first job, before any thinking happens, is translation. Take this messy, human thing, language, and turn it into clean numbers without throwing the meaning away. That's the whole challenge, and it's solved in 2 clean moves. Here's the plan in 5 steps. 1. Why letters are a problem. 2. Chopping text into tokens. 3. Turning each token into a vector. 4. How meaning becomes a direction. And 5. We watch a real sentence turn into a map live. Part 1. Computers don't read, they count. Picture the word cat. To you, that's an animal, a pet, a whole little bundle of meaning. To a computer, it's just 3 shapes on a screen, C, a T with no more meaning than 3 random doodles. The machine sees symbols, it does not see sense. And yet everything a model does, comparing, scoring, predicting, is arithmetic. So if we want a machine to work with language at all, we have to hand it language it can compute with. We have to turn words into numbers. The only question is how to do it without losing what the words mean. Part 2. Tokens, the chunks AI actually reads. Step 1 is to chop the text into pieces. Now you might guess we split on every word, but real systems are a bit cleverer. They break text into tokens, small, reusable chunks, sometimes a whole word, sometimes just a piece of one. So what is a token? A token is just a chunk of text the model treats as one unit, one whole word like dog, or a fragment like un or ing. Real example, like Lego bricks for language. You don't need a unique brick for every possible sentence. You snap a small set of bricks together to build almost anything. Why fragments? Because it keeps the vocabulary small and flexible. The model never saw the word unfriendliness before. No problem, it builds it from pieces it does know. Un, friend, ly, ness. Rare and brand new words just snap together from familiar bricks. And here's the quiet trick that makes the math possible. Every token gets a plain ID number, its spot in a big fixed list called the vocabulary. There might be token 5, cat, token 9000. Now your sentence is a row of ID numbers. We have numbers, but not yet meaning. Part 3. Embeddings, giving each token a place to live. An ID number is a label, not a meaning. Token 5000 isn't bigger or better than token 4, they're just names. So we trade each ID for something far richer, a vector. What's a vector? It's just a list of numbers, and a list of numbers is a point in space. 2 numbers place a dot on a flat map, left, right, and up, down. 3 numbers place it in a room. Real example, like a map pin, 48.8, 2.3 isn't random, it's a specific spot on Earth. A vector is a pin, just in many more directions than 2. And the embedding is the move that hands every token its own pin. An embedding is a learned vector for a token, its address in a giant space of meaning. Real example, like a seating chart for a huge party where the host has quietly arranged it so people who'd get along are placed near each other. Each word gets a seat, and the seating is not an accident. At first, every word's pin is dropped at random, pure chaos, words scattered everywhere. But as the model trains on mountains of text, it slides each pin around, nudging it a little at a time, until words that get used in similar ways end up sitting near each other. Meaning isn't typed in by a human, it's earned from usage. Part 4. Meaning becomes a direction. Here's where it stops being a list of numbers and starts feeling alive. Once every word is a point in space, two things suddenly mean something, how close 2 points are, and which way you travel to get from one to another. Closeness first. Two words near each other in the space have similar meaning. The model literally measures it as distance. Real example, like a library where books on the same subject sit on the same shelf. Coffee and tea end up as neighbors. Coffee and asteroid end up rooms apart. Nearness is similarity. But the real magic is direction. It turns out the model doesn't just cluster words, it lines them up. The step that takes you from man to woman is a particular direction in the space, and astonishingly, the very same step takes you from king toward queen. One direction quietly captures the whole idea of gender. Which means you can do arithmetic on meaning itself. Start at the pin for king, subtract the man direction, add the woman direction, and where do you land? Almost exactly on queen. King minus man plus woman equals queen. You just did math on words and got a sensible answer. And it's not a one-off. The step from Paris to France is the same step as Tokyo to Japan, a capital of direction. Whole relationships become straight little arrows in the space. The model was never told what gender is or what a capital is. It discovered these directions on its own, just from how we use words. Part 5. Watch a sentence become a map. Let's run the whole pipeline on one real sentence. The cat sat. First, tokenize, snap it into chunks, the cat sat, and look up each one's ID number in the vocabulary. 3 words in, 3 numbers out. Now embed. Trade each ID for its learned vector, its pin in the space of meaning. Our 3 little numbers blossom into 3 points, each one carrying everything the model has absorbed about that word. And step back to see the whole map. Cat lands in a quiet neighborhood with dog, kitten, and pet. Sat sits among stood, lay, ran. Similar meanings, similar places, a city of words, organized entirely by sense. That's the input every chatbot actually begins with. So here's the whole picture. A computer can't read, it can only count. So we chop text into tokens, the reusable Lego bricks of language, and give each one an ID number. Then we trade each ID for an embedding, a vector, a pin in a giant map of meaning, learned from usage. Close pins mean similar words, and directions in that map carry real ideas, which is why king minus man plus woman lands on queen. That is how AI turns words into numbers. But notice what we have now, just a map of the words you typed in. The AI hasn't said anything back yet, so how does it take that map and decide the very next word to write? That's the engine of every chatbot, and it's the very next video, how ChatGPT picks the next word. If this finally made meaning as math click, subscribe so you don't miss it. This was Glass Box. See you in the next one.